There we go. Cool. So I'm glad you both made it. As a bit of housekeeping, tutorials are you're here obviously, so every Tuesday, 2:30 to 3:30. They will be hybrid, so they'll be in person in Shaw 131, and they'll be online on this Google Meet link, same one every time. So whichever one's easier for you to join. Of course, the caveat there is that except for today where we're only online, if I'm recording while in person, or how do I say, live streaming while I'm in person, the quality tends to not be the greatest, with a mix of camera angle and university Wi-Fi. It's not usually the best, but I will offer it, and I will also record and post them on my website. So as per usual, my website is this. And I have a tab in there now for real analysis, so you can just go in there. I think I have these slides posted already. Yeah. Any questions about housekeeping before I move on? All good?
Oh, good.
Awesome. Okay, so I've got a question here about fields. I think you guys went through in the so I wrote this down. You guys had a lecture 0 and a lecture 1. So the lecture 0 was your first one, and I think you didn't really do much, but I looked through it. It seemed kind of just very introductory, basic set stuff. So probably stuff that you know from discrete math, set operations on sets, unions, intersections, set differences, things like that. So I'm not going to go over that too much unless you guys want it, but we'll go on to part 1, which you guys talked about real number axioms and properties. That's sort of the first foundation to real analysis. So I think the first thing you guys did was prove that R is a field. So you were given, I think Moran gave you a few axioms of what it means for something to be a field. And you guys just went through and proved that R is a field. Do you guys remember the axioms? The field axioms. They were the first thing you did in the second day. So lecture 1. Yep, go ahead.
I remember some of them.
Let's hear them.
Associativity and commutativity of addition and multiplication.
Yep.
Distribution of multiplication over addition.
Okay, so distribution of plus over minus, or plus over times, you said?
Times over plus.
Times over plus. Got it.
And then you need an additive identity.
Yep.
A multiplicative identity, and then additive and multiplicative inverses.
Additive and multiplicative inverses. Yep. That's all of it?
I think I've missed some.
I think that's all of it.
Oh.
Awesome. I'm just double checking, but actually, yeah, there is one mistake here. The commutativity only has to be for the addition. In our case, multiplication is commutative. It doesn't matter. It can be commutative, but I think you don't necessarily need the commutativity. It's nice if you have it, but I don't think you need it. I might be wrong. Either way, it doesn't matter in this context. I think that's all of them. So let's prove that Q is a field. We proved in class that R is a field. Let's prove that Q is a field. So, and maybe we should go through, I'm just going to pull up on my screen here the specific axioms that he used, because like they're all the same axioms, but sometimes different people will just use different like the same axioms, but just written differently or in a different sort of fashion. And you probably saw that to some degree with Mihai's course. That like when I was proving stuff in advanced linear algebra, that it might have been a little different than how Mihai did. I'm kind of wanting to keep it the same as what Moran did. So let's see. So he has the field axioms listed as closure. So I guess we forgot closure. But that's kind of almost a given. So let's go through it. So closure under addition and multiplication. So first off, actually, maybe I should do this on a separate page. Yeah, that's what I'm going to do. So closure. If I have two fractions, a over b, and I add c over d, then that's going to equal, we can do like the funky like common denominator crap. So you'd get AD over BD plus BC over BD. You can add the tops and you get AD plus BC over BD. Everyone good with that? So then we can say that's in Q. That is a fraction. I should have mentioned that. Q is rational numbers, fractions. So, we add two fractions together, we get a fraction, we're good. What about with multiplication? Multiplication is almost easier. We end up getting AC over BD just right away, which is in Q. So we have closure for both. So next, we talked about associativity. So associativity. So if we take, basically associativity means brackets don't matter, right? We take A plus B plus C, A over B plus C over D plus E over F. Well, that's the same thing, and you really should work this out if you're doing it like in full. That's the same thing as AD plus BC over BD, that plus E over F. And now it gets a bit more ugly, but that's okay. I think you get ADF plus BCF plus BDE over BDF, like that. So I just combined those fractions into one. And now from here, I can use properties that we know from real numbers, because we've already proved that real numbers are fields. So we can have associativity. And we'll end up getting, let's see, I can separate this into AD over BF. Is that right? No, that's what I want to do. Let's do A over B plus, and what do we have left over? We should have CF plus DE over B, over DF. Hopefully you're able to follow along with that. Going backwards is the hard part. Once you have this, again, you can separate them into A over B plus C over D plus E over F. And if it's any easier, what you can do is you could have started here and gone right until you get this. And then you could have started a second thought here and like worked your way back to this. So if you show that both sides equal that same big fraction, that's the same, that's like equivalent in terms of proof. Does that make sense? Any questions about associativity of addition? How would I do associativity for multiplication? Any ideas? How would I set it up? Why don't we start there? No? Okay, I guess I'll get started on it then. So for multiplication, we would do A over B times C over D, all of that times E over F. And we want to show that that's equal to, same thing if you move the brackets to the other pair. So we want to show that that is equal to A over B times C over D times E over F. Good with that? So how would I go about showing this? Any ideas? You can use the chat box if that's easier. I don't want to.
Can we just calculate it?
Yeah, it's pretty easy, right? Like it feels like almost obvious that that's true, but we're pretending like we don't know how fractions work for the most part. Like we understand some basic things, but we don't know if you can actually do that with fractions. So what we do is we rephrase it in terms of like real numbers, essentially. So what we'll do is we'll go, we'll multiply the two in the brackets first. So we'll start with the A over B times C over D. That's equal to AC over BD. And maybe I should probably write this a little bit differently. We'll do this times E over F. So it's going to equal the A over B times C over D is equal to AC over BD times E over F. Now, if I do that multiplication, I get ACE over BDF. Right? So now the top and bottom are both real numbers. They're specifically integers, but that doesn't really matter. They're real numbers, right? And we know that real numbers form a field. So we know because real numbers form a field, we can, they're associative, right? So we can re-bracket it however we want. So we'll re-bracket the top and the bottom. We'll say A times CE over B times DF, like that. Does that make sense?
Yeah.
Good. So from here, we can separate them out like this. And then we can do one more step, and it's exactly what we wanted to show. Like that. Make sense? All good? So we're done associativity. Commutativity. And it looks like he wants us to do both plus and times. So we'll do both plus and times. Maybe I'll add a new page here. Cool. Okay. So Commutativity. Commutativity means that, right, A plus B equals B plus A for any B and A in our field, or what we want to show as a field. So what we'll do is we'll say A over B plus C over D. We want to show that this is equal to C over D plus A over B. So you can swap them and it doesn't matter. How do we do this? Well, we'll try adding them. So what would be the first step? If I start with A over B plus C over D, what would be like the first step here? Go ahead.
You'd want to find a common denominator.
Sure. How would I do that?
Since you don't know what the bottom numbers are, there's always a common denominator of at least the two multiplied together.
Yep.
So you write as AD over BD plus BC over BD.
Yep. And we can add them because they have a common denominator. Like that. And now what do we do? What do we know about real numbers? Go ahead.
Since the real numbers are a field, they're commutative.
Yep,
exactly. So you swap the BC and the AD in order.
Exactly. So like that. And then from here, we can just sort of go backwards and break them back down. So we could get BC over BD plus AD over BD. And then we have like some common terms we can cancel out, and we get C over D plus A over B. Like that. Make sense? So commutativity is good for addition. We should still show it for multiplication too, but that one's significantly easier. What we would do is we would say, well, AC over BD like this, which is the same thing as CA over DB due to the real numbers. It's the same thing as C over D times A over B. So we're good for commutativity. What about distributivity? Well, distributivity looks like A times B plus C equals AB plus CB, like that. So how do I set this up? Maybe what we can do is we can go A over B times C over D plus E over F. And we want to show that that's equal to A over B times C over D plus E over F times C over D. Is that right? Oh, I got something wrong here, didn't I? Yeah, it should be AC. And then we'll get A over B times E over F. And that's what we want to show. So how do we do it? Well, the same way we did it before, right? We're just sort of slowly expanding. And maybe this time, because there's so many moving parts here, I'll do it in like 2 halves. So the first half, we can show that A over B times C over D plus E over F. We'll expand that out and we'll see what we get. So we do the brackets first. Find a common denominator, CF over DF plus DE over DF, like that. Now that we have a common denominator, we can add. So we get CF plus DE over DF. And then we can multiply. So we get A times CF plus DE over BDF. And in the numerator there, because that numerator is a real number, we know properties of real numbers, we know that we can expand that, right? We can distribute that. So we'll end up getting ACF plus ADE over BDF. Good with that? So the second side, we'll start with the right-hand side. Which maybe do left-hand side equals this. So the right-hand side, it's A over B times C over D plus A over B times E over F, like that. So what do we get? We get, using sort of your order of operations, we'll do the multiplication first. We get AC over BD plus AE over BF. From here, we can find a common denominator. So our common denominator, I'll multiply this first fraction by F and the second fraction by D. Like that. And then we can add the 2 fractions together. We get ACF plus ADE over BDF, which is exactly the same thing. Left-hand side. Do you see that? This here and this here are identical. So we've proved distributivity. What's the additive identity here? This is sort of a trick question. What's the additive identity for the fractions for Q? Yep. Good job. I was hoping you weren't just going to say 0, because that's kind of a, not a really valid, not a really valid thing to say. So yeah, 0 over 1 is right. 0 over 0 is not, because that's not a fraction, right? It's undefined. But yeah, 0 over 1 is correct. So 0, so the identity, maybe I'll write it as like the identity for plus of Q. This is just a notation I'm using. ID for identity. The subscript plus means we're doing like the additive identity, and the field that we're working over is Q. So the identity is 0 over 1. That's our additive identity. What's our multiplicative identity over Q? What fraction, when you multiply, or what's a fraction such that when you multiply it by any other fraction, it just spits out the same thing? Yeah, 1 over 1. So 1 over 1. So we found our additive identity, multiplicative identity. Now we want to find the inverses, which is usually the harder part. Yeah. So what would be inverses here? How do we figure out what the inverse of a given fraction is? Say that we have a fraction a over b, and let's say that I want to find the additive inverse of it. It's the additive inverse of a over b. So you got to be careful here. A lot of people are going to say, well, actually, before we do that, does anyone know what the multiplicative inverse is of a over b? So maybe that one's a bit easier. Or, yes. So that's the multiplicative inverse. So the multiplicative inverse of b over a, sorry, a over b is b over a. That one's not too bad. And to denote multiplicative inverse, we usually write a over b with the power of -1. That doesn't necessarily mean like anything. Like we just use that notation to represent the multiplicative inverse of something. Yeah, in this case, it literally is power of -1. But I mean, even if you think about it, like what does a power of -1 even mean, right? Like, you know, when you think about like positive integer powers, you're thinking like, well, if I raise like some number, if I raise like, for example, 3 to the power of 4, well, that's equal to 3 times 3 times 3 times 3, right? 4 times. But like, what would it mean to raise something to a negative power? That's not even really like that doesn't make any sense, right? We just define it like that. We just define that something raised to the -1 is the inverse. Similarly, we have a notation which is like negative of a fraction, and that's our additive inverse. So whenever you see negative in front of some symbol, that means additive inverse. What is the additive inverse of a over b? Does anyone know? I know it kind of seems like I wrote it, but I didn't really, because that doesn't mean anything. Go ahead.
Negative a, like put brackets on the negative and the a.
Yeah.
Over b.
Yeah. So it's like -a over b, like that, right? So it's kind of, there's a nuance there, right? The negative of a fraction, you just bring the negative in, right? So yeah, so we've shown, if I go back to the previous page there, we showed closure, we showed associativity, we did commutativity, distributivity, the two identities, and the two inverses. So therefore, we can say that, and we usually denote it like this. I think I sort of, if you were in advanced linear algebra, we might have like kind of skimmed over like the detail of how you write these things, but technically a field, and you actually will see this in one of Moran's remarks on his notes, a field is technically a set paired with two operations that work like this. So if I ask, is Q a field, that's not really a valid question because Q is not a field. Like it's comparing apples to oranges. But Q paired with the addition and the multiplication is a field. So it's kind of, again, a nuance of how we say it. But yeah, the rational numbers paired with two operations or equipped with two operations is a field. Does that make sense? So like in a sort of computer science-y context, this specific part here, this Q, is not a field in and of itself. But this like tuple, this like triple of things, the Q, the addition, and the multiplication, those three things together is what we call a field. So what you proved earlier was that R plus times is a field. Does that make sense? Any questions about this example before we move on? No? Okay. So as like I guess if you can use the raise hand feature on Google Meet, do you know what, raise your virtual hand if you know what an algebraic number is? Or what this like Blackboard bold A is. Let's see, so if we can prove a set is a field, only then it's an element from said field is scalar. Yeah, in like a linear algebra context, yeah. Exactly. And usually like a scalar is from a field. I don't think the word scalar itself, like if you just take that word, I don't think it necessarily needs to be from a field, but in the context of linear algebra, when you talk about like scalar multiplication, then yes, it has to be from a field. The scalars do come from a field. Hopefully that makes sense. Awesome. Yeah, so I'm assuming nobody knows what algebraic numbers are then, which is kind of cool. Has anyone heard of transcendental numbers? That one I think usually some math people have like heard of at some point. Anyone heard of transcendental numbers? Transcendental. Or could anyone give me an example of what an algebraic number is and a transcendental number? No? That's okay. So an algebraic number is a real number. So let's say it's well, maybe I'll write it like this. I'll say the set A, which is the set of all algebraic numbers, is the set of all real numbers x such that f of x equals 0 for some polynomial f. So in other words, you can find some polynomial that where you plug in this real number, it gives you a 0 or a root to the polynomial. Then we call those types of numbers algebraic. And maybe I should write polynomial with integer coefficients. Otherwise, that's kind of meaningless. So that's what an algebraic number is. An algebraic number is a number that is the solution to a polynomial with integer coefficients. So what can we do with that? Let's give some examples. Of algebraic numbers. Anyone have any just simple examples of an algebraic number given this definition? Go ahead.
Would you have any integer working?
Yep.
Because you could just write like x minus that integer.
Yep, exactly. So like, for example, 2 is an algebraic number because x minus 2 equals 0 has solution x equals 2. Right? All integers. Yep. So you can do that for any integer. So, you know, in that sense, you can say that z is a subset of A, right? Because every integer is an algebraic number. And maybe I'll put like subset or equal to, because we haven't really shown that there are algebraic numbers that are not integers. There are, but for now we haven't really shown that. So does anyone have any idea of an algebraic number that is not an integer? Go ahead.
E?
E is not algebraic. It's not the solution to a function, a polynomial function. So like, you can't have like there's no like x cubed plus x something x squared plus 3x or something plus 2 equals 0. Like, you can't solve that and ever get x equals e, right? So E is not algebraic. We call it transcendental. So the opposite of algebraic is transcendental. And maybe I'll write that somewhere. Transcendental is not algebraic.
Okay.
So like pi would also fit in as a transcendental number. Let's see. So like if ax minus b is a factor of a polynomial, then b over a is algebraic. Yeah, exactly. So so for example, 2 over 3 is algebraic because we could do 3x minus 2 equals 0, right? Which implies that 3x equals 2. So x equals 2 over 3. So see how we started with a function equal to 0. We solve for x, and then we get that value. That means that that value is considered algebraic. What about like when we think about things like e and pi? Another one that often comes up is like square root of 2 or something like that. Square root of some number, because it's not like rational, right? Like you can't write square root of 2 as a fraction of two things. Is square root of 2, if we take that specific example, the square root of 2, is that algebraic or is it transcendental? Go ahead.
Algebraic.
Yeah, what's the polynomial?
X squared minus 2.
Yep. Exactly. So x squared minus 2 equals 0 is a function of integer coefficients. So we can solve this. X squared equals 2. That means x equals plus or minus square root of 2. In this case, we only really care about plus because we wanted to show that that's an algebraic number. So to answer the question on the page, is it true or false that Q is a subset of A? Yes, it is. Is it a strict subset? Yes, exactly, because there are algebraic numbers that are not rational, but every rational number is algebraic. So yes, the answer to it is true. And you couldn't do the other way, right? So you couldn't, it's not true that A is a subset of Q. That's not true. Does that make sense? Cool. What's my next one? Yeah. I'm going to do this one. So let's find the error. I want you to try and find the error in this proof. This is just for general proof writing, because this course is a proof-based course, and it's, I don't think, if I remember, I don't think 2055 is a prereq for this. Maybe discrete is, but I don't know if you've had any like rigorous proof writing classes. So I want to see, well, I know some of you have because I had you in advanced, but I wonder if any of you can find the error in this proof. I'll give you some time. It's very convincing. Yep.
I think the error is in x plus y times x minus y equal y times x minus y. Here, it divided by x minus y, but because it's supposed that x equal to y, so x minus y should be equal to 0. So
Yep.
we can't divide it by 0, so it's false.
Exactly. So we can't divide by x minus y, which is 0. That's why 2 is obviously not equal to 1. So there was an error somewhere in there, but yeah, that's the problem. That was the error. I guess we have time, so we'll do question 4. Any questions about that? I assume that was pretty straightforward. It was just kind of a, wanted to see if I could catch somebody. Awesome. So we'll move forward. Question 4, order relations. So you talked about order relations, again, lecture 1. I think you guys specifically talked about greater than. You defined, or I guess you defined, looks like you defined less than as an order relation on R cross R. We're going to define a new one. It's going to be this squiggly greater than sign. And we're going to do an example with Olympic medals. So this order relation is an operator that takes in 2 countries, say A and B, and we say that we're just going to define that A is like Olympic greater than B, or equal to. If A has more than or equal to gold medals and more than or equal to the total number of medals. So you'll notice here in this example, I've given like 2 boxes. This one's the gold medals. This one's the total. First, we want to show that this is an order relation. Then we're going to use arrows to indicate the order relations between the given countries. And this is all data from the 2024 Paris Olympics. So I think I have an extra slide. Yeah, I do. Let's prove that this funky operator is an order relation. Does anyone know the requirements for an order relation? Because usually things that like, I mean, like there's a couple ways to go about them. Usually you almost want to, like you can Google them on Wikipedia. It'll give you an answer. I think the first one is transitivity. So what is transitivity? Does anyone know? What does it mean for an operator to be transitive? Negative multiplication or division changes direction is one. That's specific to like inequalities. That's not necessarily the case for all order operations. So you could define an order operation that does things differently. So for transitivity, that is, if you know that A is greater than B, maybe I'll do capitals because that's sort of the notation I was using here. And if you know that B is greater than C, then that implies that A has to be greater than C. Does that make sense? It's sort of like one follows to the other. There's a couple more. That I'm also forgetting. Let's Google them. Order, operator, I guess relation, definition. And if you go to Wikipedia, it'll give you all this stuff or somewhere else. Let's see. Seem to not be able to find Wikipedia. I guess you can't see my screen or my like computer. So, oh yeah, that's too complicated. I think additivity is one. I'm just gonna take a guess here. Additivity. We don't really have a notion of addition here, so it kind of breaks down. But we could, I guess, define some notion of addition where like you add the metals together. I don't know. If C is greater than 0, then AC is greater than BC. Yeah, that's one of them. That's one of them. We don't have multiplication again. But yeah, you could go through and define them. I'm just going to sort of leave that be for now. Yeah. I guess really the key takeaway here is that the only there's other order operations, other order relations other than greater than or less than, which are the same thing. So let's see sort of this in action, and maybe transitivity is a good one to look at. That was, I think, one of the ones you covered in the actual slides. transitivity, yeah. Yeah. So in this case, let's compare. There's a way for me to like let you sort of point, but if I number these, maybe I'll number them or label them A, B, C, D, E, F. Any idea of like if I wanted to say that A was greater than B, what I might do is I might draw an arrow like this. Any idea of which countries are greater than which here using this order relation? So remember, you say that one country is greater than the other if the country has more gold medals or equal to, and more total medals or equal to. I know there's a lot here. Could I draw this arrow from A to C? Is that correct? Yep. Thumbs up for sure. Could I draw this? This arrow here? Yep. Because, I mean, we're good on the gold medals. The total medals, 91 is equal to 91, right? Okay. Could I draw this arrow? No. Why? Did not draw this one. Yeah, because 34 is smaller than 65. What about this arrow from F to E? That one's good. Can anyone give me other arrows? Oh, I just got a bunch of thumbs ups. Cool. Any other arrows that I can draw? There's a bunch here. B to E. Yep. Sorry, that's F. B to E. It's there. B to F is also one. Kind of gave it away, but D to A. D to A. Yep, that's right. Even though the 40s are equal, they're still good. D to everything. Yep. Yep, you are correct. I'm gonna like try and do that. I think that's D to everything. Am I missing any more? What about A? If we look at A, is A greater than let's see, is A greater than E? I think A is greater than E. A is greater than B, C, E, and F. Yep, you're right. So we'll do that. What about C? Is C greater than anything? I don't think C is greater than anything because that 14 is the smallest. What about B? So far we have B is greater than E and F. Is B greater than C? think it's yes. And then we did D for E. Is E greater than, I think we got all the stuff for E, and did we get everything for F? I think we did. Looks like it, yep. So there you go. That's a diagram of the order operations. It's not directly a greater than or less than, because sometimes like there's stuff in the real world that doesn't really have a greater than or less than, but they can still be ordered in some way, right? Another order operation you might have is like alphabetic ordering, right? So we could say, for example, that like, let's see, like apple is greater than beaver because A comes before B. I don't know. Or you could say like, I'm trying to think of another good example here. Addition is greater than apple, right? We would still have to prove that this is an order relation. Yeah, you would, but you can, is sort of the long and the short of it. Again, you need to define some operations, but you totally can. Yeah. Hopefully that makes sense. And then I think one more on this language example is we could say, for example, that app is greater than apple, because like in a dictionary it would come before, right? So that is an order relation. There's different types of order relations, like I said, but yeah, hopefully that makes sense. I think that's all I have for you. For like non-real bonus points, can anyone guess what countries each of those are? If anyone paid attention to the Olympics, I did not, but no.
Is A China?
Is A China? A is China. Yes.
So D must be America.
Yep. D is America. These are actually the top 5, I guess, countries. Except for France. I decided not to include France. I think it's oh no. I'm gonna look it up because I'm gonna forget. Olympic medal counts. There we go. So it was Japan is the one with 20. It's kind of cool. 14 was Britain. What about E? E was the Netherlands, which kind of surprised me. And F was Australia. Yeah. Yeah, so that's it I have for you today. Just one reminder that next week we are back like to hybrid, I guess. We're going to hybrid. So I'll be recording, I'll be live streaming, and I'll be in SHA 131. If you have any questions, send me an email. I think that's it. Yeah. To prove this is an order relation, we would have to prove each of the properties. Yes, we would. Exactly. Exactly. I started with transitivity and then I saw the others and I was like, this is going to break down because we're going to have to like define addition and stuff. I realized I didn't have enough time really to do it. Yeah. Except that we don't need distributivity, right? So we have the axioms for order relations, which were one thing. And I think if you go back to the slides, you'll see them. They're, let's see, trichotomy, transitivity, additivity, multiplicativity. Is that a word? Yeah. Yeah. So like, what do I mean by addition? Well, for example here, how would we take like 40 and 91, like that country, which is China, and add like 20, well, let's pick a different one, 15 and 35, which is like the Netherlands, right? How would we add those two countries together? We kind of can't. Like, you can define it, right? That was why it was like, okay, we'll just throw out the order operation stuff because it's going to take too long. But yeah, you would have to define something like, maybe you might do that this sum is equal to 55 and like the sum of each of them, right? 55 and 126. Yeah. But you'd have to define it, basically. You'd have to say, well, this is what I mean when I say I'm adding China plus the Netherlands, right? Yeah. Hopefully that makes sense. Awesome. All right. In that case, if there's any questions, let me know. Otherwise, we'll see you next week.
Thank you. See you next week.
Take care. You too.
Have a good one. See you next week.
Take care.